A digital asset platform is only as strong as the risks it anticipates. In this topic, we'll model threats across smart contracts, custody, APIs, cloud, and operations, then use those insights to shape resilient, compliant architecture. Up to this point, you've built the platform layer by layer: issuance markets, architecture choices, token and settlement design, custody, and compliance controls. Now we shift from how the platform should work to what could break, who might attack it, and how the organization should respond. Threat modeling belongs inside architecture, not at the end as a security review. Start by naming what can be harmed: tokens, keys, data, decisions, and settlement authority. Then map how value and control move across contracts: APIs, wallets, cloud services, custodians, and operations. For each actor, including insiders and vendors, ask what could go wrong. Rank risks by business impact and record assumptions and controls in architecture decision records. Blockchain risk is a layered landscape, not a single security problem. At the application layer, smart contract defects can lock funds, bypass rules, or trigger irreversible transfers. At the custody layer, whoever controls keys can control assets and upgrades. Deeper down, validators, ordering, governance, and consensus create protocol-level exposure. Around the platform, bridges, oracles, and indexers can fail or be attacked. Strong architecture maps threats across all of these layers before controls are chosen. Smart contracts are more than code. They enforce issuance, transfers, settlement, and lifecycle events. So small defects can become financial, legal, or operational failures. Watch for reentrancy, weak permissions, math or precision errors, unsafe external calls, and flawed upgrades. Regulated assets also require checks for eligibility, restrictions, redemptions, and forced transfers. The discipline is straightforward. Use secure patterns, test exhaustively, obtain independent audits, monitor releases, and do not deploy without evidence. Private keys are the control point for the most sensitive actions: token issuance, treasury movement, settlement, administration, and custody. A safe custody flow begins with clean key generation and protected storage, then routes every transaction through policy checks, approvals, and controlled signing. Compromise can come through phishing, malware, insiders, vendors, or exposed backups. Monitoring should therefore watch for unusual withdrawals, bypass attempts, unexpected admin calls, and abnormal signing behavior. Digital asset platforms rarely operate in isolation. They rely on oracles for prices and valuations, bridges for cross-chain movement, and external providers for custody, compliance, banking, and connectivity. Each dependency creates a trust boundary. Bad data can trigger wrong collateral calls or settlements. A bridge exploit can destroy assets or duplicate them. An outage can halt operations. Strong controls include redundant providers, quorum-based feeds, circuit breakers, fallback procedures, vendor diligence, and continuous monitoring. Think of the mempool as a public waiting room. Before settlement, others may see who is trying to transact. Bots can copy that intent, pay more, and jump the queue, creating front-running or MEV through sandwich attacks and arbitrage extraction. In tokenized securities, this can distort prices, delay settlement, or create unfair advantage during issuance, transfers, redemptions, and DVP. Mitigations reduce visibility or discretion through private relays, batch auctions, commit reveal, permission sequencing, and careful settlement design. Finality defines when a transaction is safe enough to settle against. In probabilistic networks, recent blocks can be reorganized, so confirmation thresholds matter. In deterministic systems, finality may be faster, but validator compromise can still censor or reorder activity. In operationally final networks, governance and administrator powers become the key risk. Good architecture treats finality as a control point by monitoring the network, reviewing governance, and preparing fallback settlement procedures. Digital asset security is not limited to smart contracts or wallets. Many real breaches still use familiar enterprise paths: weak APIs, exposed cloud services, leaked secrets, and compromised software suppliers. Treat the platform as a layered system, with trust boundaries between users, services, infrastructure, data, and vendors. Each boundary needs authentication, authorization, monitoring, rate limits, secure configuration, and key protection. Blockchain controls reduce one class of risk. Enterprise discipline reduces the rest. Identity risk becomes business risk when privileged users can control assets, markets, or compliance policy. A compromised admin, custody operator, developer, or compliance officer may enable forced transfers, unauthorized changes, data extraction, or contract upgrades. Insider risk is not always malicious. It may involve coercion, negligence, or weak separation of duties. Controls should combine least privilege, phishing-resistant MFA, just-in-time access, approval workflows, audit logs, and regular access reviews, so no single identity can create outsized damage. Operational risk management turns threat models into scenarios people can own and act on. Rather than saying vendor risk, define the business event. A custody provider outage blocks redemptions, or an admin key compromise enables an unauthorized upgrade. Each scenario gets likelihood, impact, controls, an owner, and residual risk. The register then connects engineering evidence to architecture decisions, security controls, incident playbooks, and executive reporting. So risk acceptance is explicit, monitored, and defensible. Incident response in digital assets must be faster and more pre-authorized than traditional security response. Once value moves on-chain, reversal is limited, and evidence is public but time-sensitive. Strong teams define triggers, escalation, decision rights, containment, evidence handling, recovery, notification, and lessons learned before an event occurs. The playbook may require pausing contracts, freezing addresses, rotating keys, disabling APIs, or coordinating with custodians and exchanges. Communications also need preparation for regulators, investors, banks, auditors, executives, and affected customers. Resilience planning begins by deciding which services must survive disruption. Onboarding, compliance, transfers, custody, settlement, reporting, and communications. From there, set recovery targets, including how much data loss is acceptable and how quickly service must return. Technical recovery covers regions, databases, nodes, APIs, keys, and vendors. Business continuity covers manual workarounds, cutoffs, reconciliation, and authority. Finally, test the plan through failover drills, vendor outage simulations, cyber exercises, and communication rehearsals before a real crisis. The core takeaway is that risk architecture makes digital asset systems production ready. Blockchain threats and enterprise risks must be modeled together, mapped to controls, and supported by incident response, recovery, and governance. Next, we turn those safeguards into enterprise integration, DevOps readiness, and capstone design decisions.